Hello everyone and welcome. My name is Stefano Pellerano from Intel Corporation. As part of the ISSCC 2022 Circuit Insights series, in this short talk, I will give you my own industry perspective on the importance of circuit design. In particular, I would like to show you how the tremendous progress on process scaling and integration has made circuit design an incredible, powerful tool to bring new ideas to market and introduce new, exciting technologies to our everyday life. So first of all, let me briefly introduce myself. I got both my laurea degree and PhD degree in Italy from the Politecnico di Milano in 2000 and 2004 respectively. Since then, I moved to US where I joined Intel Corporation, and I am now a principal engineer specifically at Intel Labs. I love circuit design, and it is in everything I do at work every single day. My specific expertise are in the design of fully integrated radio transceivers for wireless applications and systems in deeply scaled CMOS technologies, and this includes millimeter wave and sub-terahertz phased array systems. Now, in the last few years, I've also been working in the field of quantum computing, specifically in the research and development of integrated circuits for qubit control to enable scaling of quantum computers. These circuits are very fascinating since they are intended to operate at cryogenic temperatures, often colder than deep space. As far as my career and activities, I've always been very active in the IEEE community. I've been a member of the ISSCC Technical Program Committee since 2014 and the chair of the Wireless Subcommittee since 2018. I've also been the TPC chair and general chair of the RFIC Symposium in 2018 and 2019 respectively. As fun fact, I do love speed, motorsport, and in general any type of extreme sports. And if you're wondering, this here is actually the molecule of adrenaline, very, very dear to me. To begin this journey, I would like to draw your attention on this comparison, capturing 75 years of circuit design. So let's focus on the left side first, and let's travel back in time to year 1945. This photograph here depicts the ENIAC, which is considered to be the first electronic programmable computer. So what was made of? Well, it contained 17,648 vacuum tubes, 70,000 resistors, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and more than 5 million solder joints. It was also incredibly bulky, occupying an entire floor space with more than 100 square meters and weighing more than 30 tons. And not so green either, using about 160 kilowatts of power. And you would think, with so much computer and electronics, could I mine bitcoins with it? Well, probably not at all. The computer, even it was a marvel at the time, could only perform the equivalent of about 40 floating point operation per second, or flops. And the cost of such machine, when we adjust it to 2020, would be at a staggering $7.2 million. Now, let's fast forward to 2020. And here we see a photograph of the Xbox Series X. Now, what's inside? There are actually more than 15 billion transistors in a box, which is just 15 centimeter by 15 centimeter, weighing a bit more than 4 kilograms, and using about 200 watt of outlet power. Now, how fast is this machine? The computation power is a staggering 12 teraflops, and this only at $500 price tag. Now, when we look across 75 years, the progress in computational power is mind-blowing. But even more dramatic, I think, is how accessible this technology has become. And for example, if we look at the computational cost, in 1945, you would need $180,000 just to buy one flop of computing power, while today you can get 24 billion flops just with $1. So this is really, really incredible. And the question we should ask is, what has enabled such an incredible progress? Probably considered one of the most radical inventions in human history, in 1947, Shockley, Bardeen, and Britton at Bell Labs demonstrated the first point contact transistor, as you can see here in this picture. So the first transistor was about 1 centimeter in size and already considerably smaller than a vacuum tube used at the time. The invention of the transistor per se could not be responsible for such tremendous progress in the level of complexity of what circuit design can actually do today. The additional ingredient came in 1960 when J. Last at Fairchild, following actually the key patent that Robert Noyce himself filed on the concept, built the first planar monolithic integrated circuits. As you can see here, it was a flip-flop integrating 4 transistors in about half centimeter of area. The course was then set for the circuit designer to do their magic. Transistors as the active devices implementing control switches and a process capable to integrate and interconnect many of them in a very small silicon area and with a cost that would quickly scale with large volumes. And in fact, it did not take long before Intel, co-founded by Noyce himself, developed the first commercial available microprocessor in 1970, known as the 4004. The circuit already integrated more than 2,000 transistors in a 4 millimeter by 3 millimeter piece of silicon, as you can see here in this microphotograph. And the very incredible point is that it had already achieved a comparable performance to the ENIAC. And so the 4004 actually marked a very special moment in the history of microprocessors and integrated circuit in general, since it effectively demonstrated that it is possible to build very complex integrated circuits and fit them on a chip the size of a fingernail. Now, let's fast forward to 2017. This photo here shows the Intel Xeon microprocessor. It integrates 7.1 billion transistors in a piece of silicon which is about 3 centimeter by 2 centimeter. And the computing power of this small piece of silicon is a staggering 1.2 teraflops, which is equivalent to 30 billion ENIAC computer. Just to give a sense of the level of complexity that transistor side scaling and integration have enabled, if you were, for example, to implement the same circuit or something similar with the same number of transistors, but using vacuum tubes instead, it would take more than an entire football field to just put 7 billion of them. And this is, of course, not to mention how impractical it would be to interconnect all of this together. The steady increase of transistor count enabled by scaling and integration has actually been predicted and formalized as early as 1965 by Gordon Moore, one of the co-founders of Intel. In his very popular paper, he predicted that the number of transistors on integrated circuits would double approximately every 2 years. And this, you might have heard, is also known as Moore's Law. And as you can see from this graph, plotting several integrated circuits as a function of the year when they've been released and the transistor count. And note that the transistor count here is in logarithmic scale. You can see that this law has actually been quite accurate since its inception, even until today, spanning more than 50 years of semiconductor industry. But what is the role then of circuit design, and why is circuit design so important? Well, integrating billions of transistors is pretty much meaningless without proper circuit design. And so the process technology can actually transform the silicon in the sand into the fastest transistor on the planet, but it's actually through circuit design that disruptive innovations are introduced. In fact, circuit design actually leverages the advancement in transistor technology, scaling, and integration to really bring new ideas to life. So today, if you look around you, integrated circuits are ubiquitous. And in fact, it has been said that by 2025, it is expected to have more transistors than human cells on this planet, which is, in my opinion, is just mind-boggling. So circuit design gives the opportunity to play with the most impressive Lego set, to create new technology that can really improve the life of every person on the planet. And in particular, there are endless applications today that are enabled by circuit design, and I capture only a few of them here. The evolution of computing, for example, has brought us supercomputers that are, for example, today used in data centers, or to advance science in many different fields, like pharmaceutical, for example. And of course, we have today also personal computers for our everyday life, for our entertainment, for our work, for job, and of course, they are a technology that everyone else can afford thanks to the evolution of the process technology and circuit design, as we've seen before. And circuit design has also enabled tremendous progress in IT and telecommunication. Think about today how telecommunication is important and how the technology of wireless communication allow us, to be in touch and, for example, for us to reach our cared one and families, even if they are like on the other side of the globe. Healthcare is another very important example that directly impact the quality of life of everyone. And of course, we also have automotive applications and industrial application. So in general, next time you wake up and go about your day, try to pay attention to all your interactions with integrated circuits, from your alarm clock when you wake up to your internet access and the many other things that you do during your busy day. You will immediately realize how circuit design has profoundly revolutionized our society and the way we live. And of course, we don't stop here. As a circuit designer and part of Intel Labs research and development, I have the opportunity to work on some of the latest technologies developed at Intel. Here I would like to mention two of them. The first one is quantum computing. And quantum computing is the next paradigm of computation and harness the properties of quantum mechanics to solve problems that would be untractable with classical computing. So you might wonder, where is circuit design here? Well, it's actually everywhere. First of all, we have digital circuit design, which is needed to integrate this quantum accelerator with a classical computer, a classical machine. And then we also have, due to the very nature of the quantum bits, the need for sophisticated control circuitry to generate precise analog signals and actually implement quantum algorithms. The other very exciting frontier of computing is, of course, artificial intelligence and neuromorphic computing. So here, the circuit is designed to mimic neurobiological architectures, and algorithms are implemented to emulate the human brain. This will enable the next generation intelligent devices and autonomous systems. And yet again, all thanks to circuit design. Well, this brings me to the conclusion of my talk. I hope I have been able to inspire and convince you how impactful circuit design is and will be for the progress of humanity. It's an exciting time to be in circuit design. We can leverage the tremendous progress in transistor scaling and integration to bring new ideas to life that were Unconceivable just a few years ago. So I let you go with one of my favorite quotes from Robert Noyce. Don't be encumbered by history. Go off and do something wonderful. Thank you.